WebRTC. Bit of a context since couple of you guys are joining for the first time. So we have a series of these tech sessions planned to kind of improve our engineering skills and know about the in-depth concepts. So we are trying to give you a bit of a head start on critical areas and all the basic and to get you started with these important aspects of computer science, different areas of in computer science. So we have both theoretical aspects and practical aspects of it. So what we have done is we have structured it so we will alternate between theoretical parts and practical technological application part. So last time we did a theoretical part on cryptography. So now we are going to do a bit of a practical area, which is a technology. So we are going into WebRTC. So yeah, so we'll get started on the WebRTC session. So why we picked up this topic? Because first thing, as a company, we are heavily using this. We have like I don't know five projects running using WebRTC in different ways. It's important that we know about this in depth. I know that we are using yes, audio. Okay, that's okay. Yeah. So so this is like as a company, this is a very important area of technology for us, and also in general, with all the companies moving into remote working setups, WebRTC has become a prominent technology. So wherever you go, whatever you develop, there will be a real-time communication part likely be there in that application. So as an engineer, personally, for you guys also, this would be a very important area of technology to build an expertise on. So and initially when I like look into WebRTC, I thought maybe I don't even have enough content for a 1 hour session, but it turned out to be the other way around. Like it has a huge scope, multiple different things, and so this presentation is only going to get you started on this, give you a head start, like a start, so you can get into it and then use it and build your knowledge on top of that. Since there are like variety of okay. Oh, okay. So since there are like wide area like array of different things, I'm going to structure. It's hard to structure, but I'm gonna structure this session into 3 parts. Mm, okay. So this is the structure for the session. At first we are going to kind of look at like it's going to be a kind of a top-down approach where we are going to look at WebRTC in general, like a overall view and understand what it is, a bit about its history, because it's important to have a context to understand the value of it and why it's there. And then we are going to kind of look at what does it try to achieve, and then we are going to have a look at, in the first session, we are going to have a look at the overall design decisions that they have taken. And then we are going to do a deep dive into the internals of WebRTC. And in there, we are going to look at different components and how they work together to achieve the real-time communication part. And then, there are like couple of practical complexities that they are in the practical applications, so we are going to look at those as well. And eventually I'm going to look at the browser APIs, how as a developer you can use it, like the specifics, because the other parts you won't, it's unlikely that you guys would use the other parts. It's going to be mostly on the browser API side. So as a developer, how you would utilize the browser APIs to build a real-time communication application using WebRTC. That's the last part. Okay. Yeah. All good. Right. You guys can see. Okay. Full screen. Guys, give me a minute. Okay. So the first section, what is WebRTC? So the definition that it gives is this. WebRTC is a free and open source project providing web browsers and mobile applications with real-time communication. So it's initially I also thought this is a protocol, but it turns out it's not. It's like a collection of things. So we have browser implementations, APIs, communication standards, server implementations, like multiple server implementations, and different protocols, security protocols. It's a whole bunch of things. So it's an entire project of collection of things. So not just a protocol. So that's and it's the intention of this is to kind of enable browsers to by default do real-time communication and enable developers to easily build real-time communication applications on top of browsers, and it's open source. So why did we have to develop WebRTC? Because let's so we'll look at the history a bit, where what happened before WebRTC. I think WebRTC first officially launched in 2011, but it wasn't that popular until after 2013. But before WebRTC, there were real-time communication protocols, different type of things. I'm not gonna dive into details, but if you remember, I think Skype was already there, probably in a different name. It was also a peer-to-peer communication, it used a peer-to-peer communication method. But as you may already know, all those things had problems. So as I have mentioned here, so they need a special client or a browser plugin, right? And then some of them are slow, some of them are unstable, not scalable. There were different problems with each one of them. But the biggest one was that it needed a browser plugin or a separate one. That the users did not like that. Sometimes they didn't work. But anyway, downloading something else was an annoying thing. I mean, if it was available in the browser itself, it would have been much easier. So that was the kind of motivation behind developing WebRTC. The development, actually, Google has pioneered this tech. They bought over the basic technology from a company called Global IP Solutions. They were developing the tech. Google went ahead and kind of acquired the entire company in 2010, and then they released the first completed version in 2011. They implemented it in Chrome, and then they made it open source so that others can follow. And then they worked with W3C. I think they are the ones responsible for publishing the web, maintaining the web standards. So they work with them, and there's another organization for internet protocol standards. I can't actually remember the name, but they work with these authorities and other browser vendors to make sure that this technology is widely adopted and available in every browser that we use. So that was the history of it. In developing that, so now that obviously, as we can see, it was successful, and this was hugely useful, especially in the pandemic. So I mean, Google did really good there with these efforts. So um, okay, so when they're developing this technology, they had certain goals in mind, right? Yeah. So they had certain goals in mind. These are, so primarily it was focused on real-time communication. So they wanted a very low latency way of sending and receiving data. And then it had to support audio, video, and generic data, all kinds of things. So audio, video means they had to deal with different aspects of encoding and decoding uh, video and audio streams, and make sure that all the codecs are kind of commonly available. So they wanted to work on that and find out commonly available codecs. That was one of the challenges, and the other concern was security. It had to made sure that whatever we communicate, uh, nobody can come and kind of listen to it or see the video streams that we are sending between each other. And then the wider adoption was a challenge. They made sure that they made the design available. They made the design with this concern in mind. And then interoperability, which is actually for wide adoption. They wanted to also make this available for already existing communication systems back then, especially the telecom conferencing systems that you have. So they wanted to have interoperability. That was also a concern for them. So having these sort of points in mind, they went into the design of the technology. So when designing the technology, based on those were the requirements, right? Those are the priorities for designing the technology. So to make it very low latency way of communication, they used obviously P2P. So it kind of eliminates the time between use. I mean, opposite to a server, involving a server, they went into a P2P communication because it eliminates the time that would take to kind of talk to a server, and then server talking to another peer. You go and kind of straight away talk to the peer, right? Rather than two network calls, it becomes straight one network call. Then they used UDP, which is a transport layer protocol for quick low latency communication. We usually, if you take a regular network call that you would send to a REST API, that would be using TCP. In contrast to UDP, I'll talk about it in the next slide. But so what it does is, it kind of UDP is focused on sending data fast rather than being reliable. So it's unreliable, but it's fast. But it reliability is not a concern here, because you might drop some frames in your video, but doesn't affect much. But latency affects a lot in this kind of application. So they went and opted UDP as the designated protocol for this. And then okay, so common audio video, I think I missed it. So they what I meant to say here in the second point was common audio video codecs, right? As I said, to make it widely available, different browsers uses different codecs to encode and decode audio video streams. So they had to kind of went and find the intersection of the set of codecs used, and made sure that always there would be a fallback, like a very basic level thing, where these can communicate. So they had then opted a set of codecs that would be used to kind of communicate within different browsers. And then there's this application level protocols for called SRTP and HTTPS for security. I will explain how these comes into play in the next slides. But for now, just know that for the security, these two protocols are used. And then for as you can see, all these are existing, so they try to use existing technology as much as possible. They didn't go ahead and develop everything from ground up, so it helped them to actually made it made it made it interoperate between existing kind of communication methods. And also made them easier for it made it easier for others to adopt this technology, because it was built on top of existing data. So other browsers could, they had already modules for an example, SRTP, HTTPS, and UDP. So they just have to build the top layer of this, not everything ground up. So it helped their adoption rate as well. Okay, so that is the high level idea of WebRTC. It's a low level, low latency peer-to-peer communication method. That peer-to-peer communication method that is secure and can be used without any desktop clients or any other plugins. It just works within your browser. I hope everything is clear up to now. Do you guys have any questions before we move into the next part? Anything? All good, right? Sarah, do you have any questions? Hey, well. Okay. So we'll go to the next part then. Moving on. How does it work? So here we are going to look at what are the main components of WebRTC. So not the full thing, because I don't think we have enough time to discuss it like on a very detailed level. I'm just gonna give you guys the general idea. Okay, so to make it easier for the explanation, I'm gonna break down the process of WebRTC. This is not a standard thing. I'm just Oh, sorry. Oh. Okay. So to make it easier for me to explain it, I'm gonna break it down into two sections. Not a standard thing, but so we'll talk it. So it has two parts. Assume that it has two parts. One is signaling and P2P communication. In the last section, I told you guys that this is a P2P communication method. Like a P2P means peer-to-peer. If that's not clear, I've been saying P2P. You guys. Okay. So P2P is peer-to-peer communication. So to get to the peer-to-peer communication, there are a couple of initial steps that happens in the signaling part. So we are going to first look at what happens in the signaling part, and then go into P2P section. P2P is the most complicated one with different kind of practical complexities. Signaling is rather straightforward. So I'll explain what happens here, like an overview of what happens when your browser when your WebRTC application running on the browser. What it does is it calls to your browser and get a session description. That is also kind of already available technology before WebRTC. They are just building on top of it. Session of description object. So we'll go into next step. It's easier to. So signaling has okay. I'll come back to this later. Okay, so what it does, I'll say what it does, but in general, session description object contains everything that is needed. Okay, let's back up a little bit, so that I won't make it confusing. So let's say your application creates a session description message. So that's your data about your local browser, right? So it contains different information about your codecs, your IP, and your resolution and those kind of things, and you kind of send it to a signaling server. That's the cloud over there represents. So there's a signaling server. That's a standard WebRTC implementation. So the WebRTC provides a signaling server. We can take it, and when we are building a WebRTC application, we can get that server implementation and we can deploy it somewhere. Signaling, we need a signaling server, obviously. Signaling server, um, so if you're using a managed service, they would deploy a signaling server and give give that access to you, or you can deploy it yourself. Either way, so there's a signaling server. Your app from one end kind of calls to signaling server, and then signaling server calls to the other end, and then collects data from both ends, and then both ends can share data about each other. So let's say I'm taking a call to Achala. So my browser would call to our signaling server and pass my data onto the signaling server, and then I would get Achala's information through the signaling server to my end. Likewise, Achala's browser would also get my information from signaling server. That's how we discover about ourselves. Otherwise, I don't know where to call. That's how I discover Achala's IP. So then, and also Achala's codecs, like I mentioned, and then I can figure out what is the, whether I have the, he will send a set of codecs, and I would have a set of codecs from my end. So I would then pick the most best case scenario for our communication. So that's how it would work. Then, so after the signaling process ends, so since I have all the necessary information needed for needed to establish the P2P communication, I would then call into Achala's browser directly and set up the P2P connection. Yeah.
Now caller is like trying to call the callee.
Yeah.
And caller is initially sending signaling details. Should the I mean, how does the signaling server identify the callee's detail? I mean, are we sending that in the session description? I mean,
yeah, I think I haven't looked into that much. I think it depends on our implementation. We can define a channel, and then everyone can join to that channel. That's the usual implementation. In WebRTC, they haven't
previous step to this, right?
Yeah, sort of, but I don't think it's actually a implementation that is up to us. Yeah. So WebRTC, it only gives a way to define the callee. Like it up to us to kind of figure out. I think I'll have to look into that. I don't know whether you guys got that question. So Achala was asking how the signaling server would identify where I would want to call, right? Because I would tell the signaling server I want to call this callee. Maybe let's say we are developing our own thing, so it knows where the callee is. Oh,
so that information has to be passed to signaling server.
Yeah. Either that, I think it's out of the scope. Either it already has it from like a directory, or there's a different implementation that tells it this is how you figure out the callees. So previous step. So yeah. So if I think the backend guys already worked on this, we have different concepts called channels when we are looking at WebRTC calls. But when I was looking into that, I'm also still looking into this, so I'm not sure about that. But when I look into that, there are no concept of channels in the scope of WebRTC. So they said that what they say is they leave certain things up to the developers to decide. So this is one of those areas. Yeah, we are the ones who setting up channels or whatever the concept we want, and then identify who wants to join together, right? So that's the that would be the hopefully it. You guys also look into that and let me know if that's not the case. Any more questions, or if there are any confusions, let me know. Are you guys clear on what I was saying?
No questions.
No questions. Okay. Okay. Well, I'll move on. Um, Okay, so signaling, like I said, has an arbitrary data format. This is to extend the implementation. So I think you can actually mention about certain things. So it's partially standardized because, like I said, let me go back. It has this session description, which is a standard format, but it is included inside this data format, which is so it, part of the signaling data body is standardized. And then other part they have left it to developers to customize the behavior. And then so this signaling messages contain these following informations, which is session control, so when to start and the session, and then any errors for debugging. And then network data, like my IP, I'm sending it over to the other to join now. Should I recap? Oh, I'm gonna continue, right? Okay. And then, like I said, the media codecs resolutions has to be passed so that it can resolve into a common codec formats. And this signaling process, it doesn't have to be super fast. It earlier in the earlier references I took, it only mentioned HTTPS, but like latest implementations I think also uses WebSockets for this. So it sort of make it real time, like signaling to make signaling fast as well. But early implementations just use HTTPS, so inherently it's secure, and it just has to get pass this around. So nothing critical, but it has to be reliable. So and I think that is the same thing. So yeah, doesn't matter. Yeah, and then okay, that was the signaling part. It's fairly straightforward. I think we don't have any issues about that. Signaling server implementations, I think, can be customized, and so we'll come back to this with some more in the latter part. But for now, that's it about signaling. And then once the signaling is completed, we can set up the peer-to-peer communication. So that's actually so when it comes to, so basically once I get to know about the other peer, for now we'll just consider two peers, right? Again, let's say I got to know about Achala, so I'm talking to Achala. So I got to know about his IP, his all codecs. I got it resolved. Now I'm ready. So there's a bit of a okay. I'll also come back to that later. But let's say there's a bit of security issue, but we'll discuss it later. But for now, let's assume that I got Achala's IP. I can directly now send a message to his browser. So what happens there is I send a browser requesting him to engage, right? I basically ask, do you want to talk? And you confirm me, and then we start the connection. So we kind of set up the connection, and then from that onwards we can start real-time communication. So this uses, as I said, this P2P connection. Earlier, the signaling part uses HTTPS. This uses SRTP, which is a profile. The actual protocol is RTP, real-time communication protocol or something. I forgot. Did I mention? No. Okay. So it's RTP is again an application level protocol, and RTP uses UDP underneath. Real-time transfer protocol. Okay. Okay. Real-time is one word. Okay, so RTP stands for real-time communication protocol. Transport. David. Okay, so RTP uses UDP. Like I mentioned, UDP is very fast but unreliable protocol. So to make it a bit clear, I'm gonna. This is the comparison to your normal network call. So, as you know, internet internet is like the internet. The technology of internet is like stacked, like has 7 stacked. What do you call it? Network stack. So network stack has 7 layers. These are the. Is there a stack on top of application layer? No, right? Application is the topmost layer, and then underneath that there's transport layer. Underneath that network layer, right?
Presentation layer.
Yeah, presentation layer is there, but you can eliminate that. Yeah. So
there are several interpretations like taking presentation into the application layer.
Yeah. But I mean, they actually later figured out that most of them are redundant. Yeah. Actually, the ideal network stack should have been 3 or 4 layers. They are. The big tech companies are also working on eliminating those, I think. So that's additional stuff to know about. But anyway, so here's the. So I haven't mentioned the networks underneath. Obviously, after transport layer, the everything that is used here is common. So network layer uses common set of protocols, but on top of that, a normal application would use HTTP or HTTPS. Here we use RTP instead, and RTP has different profiles. So SRTP is a secure profile. So it obviously encrypts the data before sending them through the network. And then so RTP is already designed to use UDP. So WebRTC didn't have to do anything there. RTP inherently uses UDP, so it's fast.
WebRTC initially used HTTP.
No. That was for signaling. So signaling part initially used HTTPS, but recently they have also adopted WebSockets. But don't this is P2P has always been through RTP, very specifically SRTP. And on transport layer, normal network code would use TCP, which is reliable, but
overhead is high.
There's a huge overhead to make sure that everything gets there in order. And you've seen the memes, so I don't think I need to explain. Yeah. So moving on. So P2P also, as I said, in the ideal scenario, that's what I mentioned here, like while ago. So you just start signaling to the server and then just talk to the peers, set it up, communicate, right? This is the ideal scenario, but there are complications in practical world, right? Specifically when there are NATs in between, right? So to explain, WebRTC is designed with that in mind, right? Asya natin na ko. Yes. Okay. Right. So when there are nets in between, things get complicated. So before I went into net solutions, I'm gonna explain net a bit. Net is actually network address. Net stands for network address translations, right? So when we are connecting to internet, our devices, like nowadays, our devices don't get a public IP. That means our IP, what we get is local to our network. This can happen within our like local Wi-Fi network or at ISP level. It can happen at different levels. We don't know, but usually there's definitely a net in between us and the internet, right? So what it does is it kind of tracks our local IPs, and our net device has a public IP. So it when we talk to a server on the internet, our request goes through net, and since net keeps track of where the requests are coming from, so it can when we send a request to a server, it goes through a net, and then when the request comes back, net knows where to send it back. So net keeps track of this through ports, I think. Yeah, ports and IPs, local IPs. So let's say I'm using this client. So 0 point, yeah, point 2. First one is fixed 02. It will keep track of what I'm sending and where it's going. And then when the server sends it back, it actually sends the packet to this net device, because server sees the net device. It doesn't see our device because we don't have a public IP. You have to, when to communicate with the internet, and you need a public IP. But since we
it's like identifier, right?
identify, yeah. So whenever we are communicating through internet, everyone needs identifier, but they are doing it to save the address space, right?
Yeah, but mainly and
Security
for
purposes,
security as well.
for security purposes, and
But
to
the reason why IPv6 is not popular is
because of that. Yeah. So they do that to actually to have a more control over not local networks, and to kind of have save their address space, so they don't have to allocate a public IP for every device. They can just have one device that has a public IP, and that device can track others and manage it. So that's basically NAT. So what is the problem here? When we establish a peer-to-peer connection, like I said in the earlier signaling step, we send our IP to um, our signaling server, right? So when we are sending our IP, what we see is our local IP, not the public IP. So if I send my local IP to signaling server, and then if okay, that's the solution. So we stick here. I think one side is missing. So yeah, but anyway, I'm gonna explain it with the other side. So yeah. So network at because of net, um, um, yeah. So because of net, when I send my own IP to signaling server, what I'm saying, if I just send my IP, what my signaling server would get is my local IP, and then it would uh, send it to my callie, but then callie wouldn't be able to connect me through my local.
probably call another device inside.
Yeah,
His own
callie would call another device in their local network if my IP is already repeated there. Very likely scenario,
Yeah.
but that's the problem, right? I don't see my public IP, so I cannot actually. So others can't. So likewise, if they send their local IP, I cannot get to them because public IP is different. But if I knew their net IP, this is possible. So I can just talk to net, and maybe, so if So if they would send their local, both their local IP and their net device IP, that would be possible. So uh, that is our first solution for NAT, right? So there are two solutions for NAT. Actually, stun is the priority one, uh, turn is the fallback. So if there are NATs in between, the first priority. So I'll use the I'll explain the priority order later. But to get started, stun is the first solution. So it uses something called stun server. Like I said, another component of WebRTC, it's a server implementation. It's very simple. It's called the echo server also. What it does is when we call to that, when we send a request to that server, obviously when I'm behind the net, it goes through my NAT device. So it sees my NAT device's public address, so it kind of responds with that address. So I get to know my public address. So
usually when devices within a local network, they don't see the net table, right?
no, they can't.
They don't have
Because of the security reasons, NAT device wouldn't allow them, right? Public IP. I think sometimes it may be possible, but we cannot rely on that. So it might be, we might be able to kind of figure out our public address by calling to our NAT device, but we cannot assume that it's always there or it's always allowed. So the best option is to use a stun server. So stun server sits outside. It's also in the network like internet. So I send a call to stun server through my NAT gateway, and then when I get the response, I get to know my public address, public IP address. Then I send it to signaling server, and then again your PS would know your actual IPs. So so this also can fail in some situations for certain. I'm not sure. Again, I'm not sure about the exact details, but due to some firewall configurations, this also can fail. So when that fails, we use a turn server. So basically, it's uh, another server. Again, it's a WebRTC implementation, standard implementation. There's a there's a code base you can get and deploy. So that server act as a repeater for me, and it has a public address. So I talk to that server, and that would connect to my peer. So that would either make a peer-to-peer directly with my peer, or that peer would also have another turn server. So turn servers would talk to each other. We don't know what's going on there, but from my end, I can guarantee that I would if my stun fails, turn would be there. But having a turn server is optional. We could not have a turn server. So in that case, if stun fails, your call fails. Can't help. So I think most of the free services like Google Meet doesn't have a turn server because the cost is very high. Because for each one they have to handle a huge bandwidth. As I saw, they don't provide that. But if like it's a critical thing, you will have to use a custom implementation with turn server. Mm, yeah. Uh, okay. Yeah. So then there's this framework called ICE, not the drug, Interactive Connectivity Establishment. So this is the framework, not a protocol. Actually, it's a framework. So so it actually handles this. So it actually looks at um, multiple things. So we have to try stun. We have to so we have multiple ways of connecting. So first priority. So it kind of like I said. When there's a net or a firewall, we have to connect through stun. If stun fails, we have to go into turn. So those things, how this is handled through ICE. So ICE handle it like this. So they give first priority uh, to establish a direct connection between peers. So it doesn't. So if there are no nets, uh, then I can directly. So if both peers have public IPs, they can directly communicate, right? In that case, they wouldn't use stun. They would directly go and connect between two peers. If that's not possible, it will try with stun and try to find out the public address of the nets and then connect via that. And if that fails, if the turn server is available, it would go and try to connect through that. But the like I said, this keyword here is priority. So keyword is a priority because it's not an order. Actually, it ICE actually does all three things parallelly. To make sure that you connect fast, uh, so it kind of tries out all these things in parallel, and if the first one is available, it gives priority to that. So it actually what it does is, in the first step, it doesn't care about actually finding out whether we are behind a net or not. It just straight away go and so are you good? Okay. Just to recap, so IC is the framework. IC is the framework that IC is the framework that handles different kind of connecting methods. So we have, whether we are going to go with stun or turn or that, ICE handles. So it kind of parallelly tries out all three steps and figure out best way to go. So obviously it gives first priority to direct connection. So if both have public addresses, or if both are in the same network, it connects. So it just tries with the IP that it sees first. So it can be in the same network, it connects through the local network. If it connects, that's fine. It also tries to find out parallelly. It also tries to find out the public address through stun. But if it fails, if there's a turn, it would communicate via turn. Yeah, so that's the ICE framework for you. Okay, so that's the overall communication part of WebRTC. But before we come to this point, do you guys have any questions? No. All good. GPS එක. What does turn do?
මොකක්ද කරන්නේ? කොහොමද? No. Turning කරන්නේ අර ඔක්සියක් කරනවා. Okay.
Are we going to take a break or we'll continue? Okay. So anyway, we have so we talked about communication and security in general. So we talked about a lot about security, how it encrypt messages, but we didn't talk about authentication, right? When we are, so in this context, authentication is establishing the originality of the callers, my peers, right? When someone's calling me, I have to first figure out who's calling, and I have to establish whether they are the ones they are claiming to be. They are actually ones they are claiming to be. So how does this work? This is out of the scope of WebRTC. But it provides provisions to do this, but it doesn't specify how to do it exactly. So it has left it to developers because there are different ways to authenticate. But as I saw, it's kind of tricky area. I'll have to look in more into that. But it does authentication at the signaling level, and then at each peer they kind of validate whether these are the right callers. They have kind of a, they can use different kind of mechanisms. Yeah, tokens, sign tokens, and then they validate. So it's totally up to the implementation to figure that out. That about authentication. And the next step is topologies. When we have peer-to-peer calls, so far we only considered just two peers. So it's very obvious topology in this two peer scenario. But when we go into multiple peers, what happens, right? So if like so this is the obvious case is everybody talks to everybody, right? So and for an example, in this call, uh, uh, we might be talking to all of other individually, might not, right? But as you can obviously see, this doesn't scale well, right? If like when the number of devices increase, the number of connections increase exponentially. So you can't rely on this one. So there are different kind of things that you could do. So this is one where you can do this. So in that you can configure the WebRTC implementations to connect to one device. So one device should broadcast to uh, one device should connect with all others and uh, communicate, act as a bridge, so that it can communicate with different kind of uh, with different peers. So it would save bandwidth of lot of guys, uh, but it might not be reliable because then if this central device goes down, everything goes down, and this is too much load on the central device. So we have again solution for this. This is large. When there are large number of implement devices connecting to a call, there's a server in the middle. This is also a standard implementation of WebRTC called WebRTC Media Server. So I think in our we had this kind of issue in uh, one of our projects. So how to handle it when there are like large number of participants in a call. So the solution for that is to go and implement a media server, and then configure your WebRTC implementation to use that media server. So it's also available, like readily available with the server. Um, you can just deploy it and let your peers know that they should connect to the media server, not to each other, right? So then media server would handle the bandwidth. So in I think in Needle we had this issue because it's a mobile. So for people who doesn't know it, this it's a mobile device that is broadcasting to thousands of users. Obviously, the mobile device won't be able to establish connections. In that case, um, we should deploy a media server, and then mobile device should connect to that, and the server would broadcast it to other devices. Obviously, we didn't know that uh, that part. It's just that we used a managed service. They actually handled that. When we told them, they would. I think it automatically picks up the situation of it, and it automatically handles. But this is how it works, and this information would be really useful when we are deciding on implementations of uh, different applications. I think a couple of you guys did a case study with us, where this was one of the stacking points.
Maybe pick the right managed
Yeah.
service.
And also even when we are using managed services, we need to sort of verify with them that whether they are doing this, or how they are doing this, whether that this particular thing is available. So knowing this thing is crucial. Yeah, so that's it about how this technology works. So we are running out of time. I'll quickly go through the next section also. How do we use this um, technology? So to use it, I'm only going to focus on the browser side, because servers pretty much all the server implementations are available, readily available. Those are standard WebRTC implementations. We can just deploy them and use it. But on the browser side, just to give you an idea, so this is the browser architecture. So we are going to discuss about the usage from the browser, basically from a front end perspective, how to develop a WebRTC application. So when we use a managed service, most of these complexities are abstract away from their SDKs, but it's important to know what's inside. I mean, while I'm looking at this, I also find it out the use case that would have been helpful back then while we are using one of the SDKs. I'll mention that as we go. But anyway, this is WebRTC implementation. It has so this green part is the WebRTC implementation within browsers. So it has some overrideable parts. It has a video engine, voice engine, and transport layer complications. It handles everything. Don't have to worry too much about this. Just to give you an idea about this. So and it has this one on top of the green one is the layer for web developers. That's what we are going to discuss here. Everything else is for browser developers to worry about. But commonly, your JavaScript application can talk to this web API and get everything done related to WebRTC. So when they are designing the browser API, they have broken it down into three main parts. One is acquiring audio video. Basically, it's just getting access to the user's audio video streams through browser, because whatever application that we develop, it runs on top of a sandbox in the browser. We cannot go and directly access video or audio. We have to request the browser, and then browser handles acquiring it, and then it kind of relays it back to us. It just focus on acquiring audio video, and then the other part is communicating audio video, again different section, and then we have communicating generate data. Yeah, so moving in. Okay. So acquiring media is called that section of API is called media stream, or the method is actually get user media, and then communication for audio video is RTC peer connection, and then communicating generic data is RTC data channel. Pretty straightforward. Okay, so media stream, it obviously returns audio video streams, and it actually, the most important part is it handles the user permissions. So when you are using this API, it kind of gives that pop-up to the user to allow the application. So it says that this application is trying to access your media streams, and then when user allows that, it gives us access to users media streams. So those permission level complexities are abstracted away by this. So this is the method. What do you call this? Yeah, function, or I don't remember the word. Okay. Anyway, so this is how you call the media stream method. So get user media constraints, and you have a success callback and error callback. Constraints, obviously, I will talk about constraints in the next step. So apart from this, it can have multiple audio video tracks, and you can actually turn video off. I think audio is anyway is there. You can turn on or off video. So video is optional. That's how it works. So you can in here you can define what to do in the success. You can get the stream here, and so in here it is attached to a video so that it displays it. You can, so this is implemented in a way that whether you want to display, or whether you want to send it without displaying. So they have made it flexible so that we can do whatever we want. We can directly send it to our peers, so we can just display it for the user. We can do whatever we want with it. It just gives us access. So in constraints, uh, we can specify different kind of things, very specific, um, resolutions, min width, min height. So this was actually would have been very useful when we were developing XtraView, because the AWS team claimed that they are not handling resolution, but actually they should be handling, or at least they should give us a way through their SDKs. But their support claimed uh, that they are not handling the resolutions, but which is actually a big fat lie. Now that I see. Yeah. So yeah, so we've been using their SDKs, and they claim that resolution is not configurable, which is not the case. Yeah. So we can control different types, media types, resolutions, frame rate, all sort of things. So when acquiring the media streams, we can enforce lots of constraints here. Okay. So and then we have RTC peer connection, which handles the audio video part. So it abstracts away everything from signaling to forming the P2P connection, to codec management and security, bandwidth management with throttling. It abstracts away everything and just gives us one call. So in here, this is the call. In here we have a server object and then set of options. Server object specifies whether there are media servers, like I said, or where our turn servers is, or where our signaling server is. First of all, the signaling server should be there, so it specifies that. And then our stun server, if there are any, and then if there are any turn servers, we can specify it here. And then optionally, if we are using a media server, we can also specify it here. So everything is we can mention, and then initiate a connection. It would signal to other peers and then form a direct connection between other peers. So this is just a code example where it. So this is basically making a connection between someone, connecting to someone. So it has. Wait, let me go back. Okay. We can set callbacks to handle different kind of events, like making an offer, receiving an offer, or setting when what to do when a connection is formed. So all options are there. So you guys can maybe go ahead and, so I'm gonna skip ahead, but you guys can obviously they have good documentation. You can go and study and figure out what each of these does. Okay, and then we have RTC data channel, which is again which is they have made it intentionally similar to API, similar to WebSockets. So we can use it as same as similar to WebSockets. It can either be reliable or unreliable. So I'm not sure, but I think they make the reliable happen through at the application level, because it also uses the same SRTP connection, which is unreliable. So on top of that, they have enforced a reliability metrics. So it depends on what we want. They actually some of them, this is used to some of the gaming in the browser, peer-to-peer gaming. So in those cases, it has to be fast. In that uh, when that is the case, they opt for unreliable. But if we want to build a chat or something, we have to make it reliable. So that's also an area that we need to look at, because most of the SDKs don't specify this, especially when we also uh, whether we were also considering in one of our applications to record some of the user interactions in ExtraView. But I think the people who worked on ExtraView knows this. We were considering data channel to capture certain user interactions, but we didn't looked at whether it's reliable or unreliable, which should have been crucial. Luckily, we didn't go for that. If it was unreliable internally, it would have been a problem because we needed reliability there. So these are the things you should consider when utilizing this for building applications. So anyway, this is a ultra low latency secure data channel for whether you can use it reliably or unreliably. Yeah, so this is how it works. Basically, you can use the same RTC peer connection, and when this is formed, you can use this on data channel to register. I'm also looking at this now. Yeah, yeah. So you can set up certain callback functions to receive messages and send messages. Okay, so you can use this. So here we are, I think, setting up the. So this part is for setting. You guys can see my mouse pointer, right? Oh no, probably not. Okay, so PC.on data channel means receiving the. So there we define. So basically, we register a callback there. PC is the peer connection that we formed in the first line, and then after forming the peer connection, we go ahead and register what to do when a message arrives. In here, we are actually selecting a div, and we are going to display that data in that div, and then then in the next section we are calling a create data channel method, so that you get a send channel object, which then you can use to send data. That's what so that's what happens in the last part. Basically, we are binding it to the UI so that whenever this send button is clicked, it will send the data through send channel.
Excellent.
Yeah, I think the code is pretty self-explanatory. Okay, so that's it about the browser implementations. So I'll also give you guys a bit of resources. This is an outdated list that I stole from an older presentation. Actually, lot of the content I got it from 2013 Google I/O event presentation. So they after they launching in 2011, they were trying to popularize it by 2013. So they talk about this, and they show a lot of things that this can do in 2013 Google I/O event. So they have a separate deck. If you didn't understand any of this, you can go back and refer that. It's a very resourceful presentation. The video is also there in YouTube. So this what they say is basically even in 2013 Chrome had implemented it, but Firefox is on beta, and Microsoft is also getting started, and Apple probably implemented it like 5 years after that. I don't know. But that's the case. So in that presentation, they gives out some of useful resources for implementation and debugging your applications. Most important one is this: there's a built-in debugging tool in Chrome. So you can actually go to Chrome and go to this address, which will show the diagnostics of your WebRTC call. I think we can actually try it here.
You want to sharing the link?
Let me see if I can go there first. Ah, okay. So this is stats for our code. You guys can see, right? So this is my Chrome Web Internals uh, uh, details. I think it shows all the events that happens in the call. I don't know most of how to interpret most of this. I'll have to look closely into this. But yeah, so I think this would come in handy when we are debugging the applications. I mean, so it shows. I think for each participant or each connection, it shows packets sent and packets received and bytes and all those stuff. Selected candidate. I don't know what these are honestly, but
Peer connection? No. Could be.
yeah, I think these are peer connections, right? How many peers are there, and maybe we can get an idea about the topology of the application. I think not everybody is connected to everything. That's okay. So remote inbound RTP, there are remote inbound RTPs, and then there are remote outbound RTPs and peer connection. Okay, I don't know. We'll have to look closely at this. Also, there are two things. I don't know. Anyway, when we go into this, this will be definitely useful once we started using it. I have never used it, but when we are working with obviously working with advanced applications,
Peer connection for screen sharing and
yeah, probably we have two connections for the screen. So she got stuck. Oh,
that's a problem with Chrome.
okay.
Now,
Okay, I think so. Laptop got stuck. I had to close Chrome internals. You guys can still hear me, right? Are you guys even there?
yeah.
Okay.
Yes, yes.
I hope nobody fell asleep. Okay. Anyway, so that's it about Chrome Dev Tools. Try to figure out what's what. You know, when we are going deep into the tech implementations, and then
Stop share.
wait, I have to reshare this site. Let me go back to the presentation. Okay, so we are almost done now. So these are a couple of more resources if you are building your own application. We didn't need this because we were using all sorts of SDKs provided by different service providers. But if you are building our own thing, we would need this. WebRTC specifications keep changing, and then on top of that, there are like slight differences between browser implementations. Adapter.js basically handles and move out all the complexities, and use JavaScript polyfills to make sure that there is a consistent API for developers to uh, you know make use of uh, for their applications. And then there are certain JavaScript frameworks. Um, like I didn't get opportunity to go through everything, but this is actually to uh, make it easy for development. There are like set of JavaScript frameworks, and then there are server implementations. But if we are developing our own thing from ground up, this could be um, useful. Some of them might, like I said, might be outdated because this is from a 2013 deck, but that's and there are definitely there will be newer tools available, so you guys can go check those out. But the fundamentals are the same. Okay. Any questions, guys? Anything? Uh, I'll then start asking questions. All right. So if there are no questions, we'll wrap it up. So right. So okay, we'll wrap up. Thank you guys for joining in. Yeah. So I think we'll put all of these recordings to one place and share, so everybody has access to it and go back and refer it. Because I mean, we don't expect you to like absorb everything from this session. This is just a start, so whenever you need, you can go back and refer those things, and you can study on your own. I hope this will give you like a start to kind of go and tinker with this stuff. If you have time actually and you are interested in this, go and try to set up your own thing. There are a lot of tools available. I think there are also readily available signaling servers, so you can just implement your JavaScript applications and then use those to connect with different things, and try out different things. So hope this will give you a start, and so we'll see regarding tech sessions. We'll see whether we can collect the recordings into one place. So that's it for the tech session. Next one is also planned. I think next one will be on blockchain as a URL. So we'll finalize the date.
Yeah, blockchain expert.
Okay. Maybe Rusiru can present. Okay, Rusiru and Dinu can present. Okay. So we'll finalize on that and let you know, guys. So we'll see. Okay. Okay. Thank you, guys. Have a great have a great evening.
Thank you.
Refresh. Sorry.